In the previous video, you have seen that the roots of the auxiliary equation all are distinct. Now we take that case if the roots of the auxiliary equation are equal. If the auxiliary equation, if the auxiliary equation has equal roots, has two equal roots, two equal roots, m1 is equal to m2, then the general solution, then the general solution of linear differential equation with constant coefficients reduces to y is equal to c1 e to the power m1x plus c2 e to the power m1x plus c3 e to the power m3x plus and so on cn e to the power mnx. You can see if two roots of auxiliary equation are equal, suppose that two roots m1 and m2 are equal, then the general solution of the nth order linear differential equation with constant coefficient can be written as y is equal to c1 e to the power m1x plus c2 e to the power m1x plus c3 e to the power m3x and so on cn e to the power mnx. Now we can see here this e to the power m1x is common, so this can be written as c1 plus c2 times e to the power m1x plus c3 times e to the power m3x and so on cn times e to the power mnx. You can see if we take linear differential equation with constant coefficient of nth order and the auxiliary equation have two equal roots, suppose m1 is equal to m2, then the general solution of that linear differential equation with constant coefficient can be written as y is equal to c1 e to the power m1x plus c2 e to the power m1x plus c3 e to the power m3x and so on cn e to the power mnx. Now we can see here e to the power m1x is common, so we put here a is equal to c1 plus c2. So this can be written as y is equal to a e to the power m1x plus c3 e to the power m3x and plus and so on cn e to the power mnx. You can see here the arbitrary constant are n minus 1 because arbitrary constant is a, c3, cn. There are n minus 1 arbitrary constant where a, c3, c4 and cn are n minus 1 arbitrary constants and the differential equation is of nth order and the differential equation is of nth order, which is not possible. You can see here if we take two equal roots of auxiliary equation, suppose that two roots are equal, that is m1 is equal to m2, then the general solution of the linear differential equation with constant coefficient reduces to y is equal to c1 e to the power m1x plus c2 e to the power m1x plus c3 e to the power m3x and so on cn e to the power mnx. Now we take common e to the power m1x, this can be written as this one. Now put A is equal to C1 plus C2 because C1 and C2 both are constant. So C1 plus C2 is also constant. This is equal to A suppose. So this is the general solution of the nth order linear differential equation with constant coefficient. Here we can see A, C3 and Cn. There are n minus 1 arbitrary constant and the given differential equation is of nth order. So this is not possible. So this is not possible. This is not possible, that this cannot be the general solution, cannot be the general solution of linear differential equation of nth order linear differential equation with constant coefficient. Constant coefficient, because we know that in nth order linear differential equation with constant coefficient, general solution always have n arbitrary constant, and here we can see there are n minus 1 arbitrary constant. So this is not the general solution of the nth order linear differential equation with constant coefficient. Now we consider a differential equation d square y minus 2m1 dy plus m square y equal to m1 square y equal to 0. Now we consider the differential equation d square y minus 2m1 dy plus m1 square y is equal to 0. Where this capital D is equal to d by dx. Now this can be also written as d square minus 2m1d plus m1 square y equal to 0. Now we solve this, we factorize this. You can see here this can be written as, this is whole square of d minus m1 y is equal to 0. Here we can see that d square minus 2m1d plus m1 square can be written as d minus m1 whole square y. And d minus m1 whole square y, this can be also written as d minus m1 multiplied by d minus m1 y is equal to 0. So put d minus m1 y is equal to v. So above differential equation reduces, d minus m1 v is equal to 0. Now this can be written as dv minus m1 v is equal to 0, and d is d by dx, so this is dv by dx minus m1 v is equal to 0. We can see here this is the first degree differential equation. So using here variable separable method, so this can be written as dv upon v is equal to m1 times dx. On integration we get here log v is equal to m1 is constant and integration of dx is x, and we take here constant log c1. Log c1 is the integration constant here. Now we can write this log v minus log c1 is equal to m1x, and using here property of log, so this can be written as log v upon c1 is equal to m1x. So this can be written as v upon c1 is equal to e to the power m1x. So v is equal to c1 e to the power m1x. Now we can see here v is equal to d minus m1 times y. So here we write d minus m1 times y is equal to c1 e to the power m1x. This can be also written as dy minus m1y is equal to c1 times e to the power m1x. dy can be written as dy by dx minus m1y is equal to c1 e to the power m1x. You can see this is the linear differential equation first order first degree. First order first degree. So we solve this linear differential equation first order first degree linear differential equation. First we find out integrating factor. So integrating factor is equal to e to the power integration. Here p is minus m1 times dx. Now minus m1 is constant and integration of dx is x. So integrating factor is e to the power minus m1 x. Now the solution of the above differential equation can be written as y multiplied by integrating factor is equal to constant c2 integration integrating factor multiplied by q dx. Put in value of integrating factor here, so we get y times e to the power minus m1x is equal to c2 plus e to the power minus m1x, and q you can see here, q is c1 e to the power m1x. You can see here this is q. Because we compare the given differential equation, this dy by dx plus py is equal to q, where p and q both are the function of x, where p and q are function of x only. So you can see here c1 is constant, so it outside the integral sign, and here e to the power minus m1x and e to the power m1x, this will be e to the power 0 and that is 1. So here is dx, and the integration of dx is x here, so y e to the power minus m1x. We can write this c1x plus c2 times e to the power m1x. So this is the solution of the given considered differential equation d2y minus 2m1 dy plus m1 square y equal to 0. Here you can see that the roots of this auxiliary equation are equal, because here the roots are equal roots are m1 and m1. So the solution can be written as y equal to c1x plus c2 times e to the power m1x. You can see here this solution has two arbitrary constants, and we consider here the second order differential equation. If we take third order linear differential equation with constant coefficients, so the general solution is y equal to c1 x square plus c2x plus c3 times e to the power m1x. Here if m1 is equal to m2 is equal to m3, if three roots are equal and the given differential equation is linear differential equation with constant coefficient of third order. If the third order linear differential equation is given and three roots are equal m1, m2, m3, then the general solution can be written as y equal to c1x square plus c2x plus c3 times e to the power m1. Similarly, if we take nth order linear differential equation with constant coefficients and k roots are equal and n minus k are distinct, then general solution y is equal to c1 x to the power k minus 1 plus c2 x to the power k minus 2 plus and so on plus ck x to the power mx plus ck plus 1 x to the power m plus 1x, and so on c n x to the power n x. So this is the general solution if given nth order linear differential equation with constant coefficients. Now we take one example of linear differential equation with constant coefficient in which roots are equal. So first you can see this differential equation can be also written as dqy minus 3dy plus 2y is equal to 0. And this can be also written as dqy by dx cube minus 3 dy upon dx plus 2y equal to 0. You can see this is the linear differential equation with constant coefficients, and this is of third order. Here we can see this is third order linear differential equation with constant coefficients. You can see here the coefficient minus 3 is constant, here the coefficient 2 is constant. So this is linear differential equation. This is linear difference. This is third order linear differential equation with constant coefficients. You can see here this is third order linear differential equation with constant coefficient. So this can be written as d cube minus 3d plus 2 times y equal to 0. First we find here auxiliary equation. Now we replace m in place of d, we get auxiliary equation m cube minus 3m plus 2 equal to 0. You can see here when we find auxiliary equation, put d is equal to m. In place of d we put m. So this is m cube minus 3m plus 2. We solving this. So put m is equal to 1. If we put m is equal to 1, we can see here 1 cube minus 3 multiplied by 1 plus 2. So 1 cube is 1, here 3 plus 2. So this is minus 2 plus 2. So this is equal to 0. So m minus 1 is the factor of the above equation. So m minus 1 is the factor of the above equation. So we can write this m minus 1 3 times, and you can see here we find out m cube. When we multiply here m by m square, we get m cube. When we multiply this m square by minus 1, we get minus m square, and there is no m square term, so we write here plus m. So plus m multiplied by m, we get plus m square, and this minus m square is cancelled out. Now this plus m multiplied by minus 1, we get minus m, here this is minus 3m. So 2m is remaining, so multiply here 2. So this minus 2 multiplied by m, we get minus 2m, and this m multiplied by minus 1, we get minus m. So minus 2m minus m will, this is minus 3m. And when minus 2 multiplied by minus 1, we get plus 2. Now we taking common. Now we taking common here m minus 1. So we get m square plus m minus 2 equal to 0. Now we factorize this m square plus m minus 2. So this can be written as m square plus 2m minus m minus 2. 2m minus m, this is m. Now we taking common here m, we get m plus 2 in bracket, and taking common 1 here, we get m plus 2. Now we taking m plus 2 common here. So in the net bracket we get m minus 1. So the roots of the given differential equation is 1, 1, 2. So the general solution of given differential equation is y is equal to, you can see there are two equal roots, 1, 1. So we write here c1x plus c2 and e to the power 1x plus c3 e to the power 2x. So this is equal to y is equal to c1x plus c2 e to the power x plus c3 e to the power 2x. So you can see that in this example there are two roots 1, 1 are equal. So we write the general solution. We take second example. You can see here this is the fourth order linear differential equation with constant coefficient. Here minus 7 is constant, 18 is constant, minus 20 is constant and it is also constant. So this is the linear differential equation with constant coefficient of fourth order. So this is fourth order linear differential equation. This is linear fourth order. This is fourth order linear differential equation with constant coefficients. So you can see that this equation, this differential equation can be also written as here d by dx, this is equal to capital D. So this can be also written as d4y minus 7 d cube y plus 18 d square y minus 20 dy plus 8y is equal to 0. In place of d4 upon dx power 4, capital D to the power 4, here d cube y by ds cube can be written as d cube y, d2y by ds2 can be written as d square y, and dy by ds can be written as dy plus 8y. Now we taking common here y, we get d4 to the power 4 minus 7 d cube plus 18 d square minus 20d plus 8 and y is common here. Now we find the auxiliary equation. When we find the auxiliary equation, replace d by m. So the auxiliary equation is m cube m to the power 4 minus 7m cube plus 18m square minus 20m plus 8 equal to 0. Now we find the roots of this fourth order equation. So this is the biquadratic equation. So first we find the roots of this biquadratic equation. So if we put here m is equal to 1, if we put here m is equal to 1, you can see put here m is equal to 1. So this is 1 to the power 4 minus 7, 1 to the cube, 18, 1 square minus 21 plus 8, this is equal to 0. Here 1 minus 7 plus 18 minus 20 plus 8 is equal to 0. So this is 18 plus 8, this is 26, 1, 27 minus 27 equal to 0. So m minus 1 is the factor of above equation. You can see here if we put m equal to 1 in this above equation, in place of m we get 0. So m minus 1 is the factor of above equation. Now we factorize this biquadratic equation. So m minus 1 right here 4 times. You can see here we get here m to the power 4. So we multiply here m cube. If m cube multiplied by m, we get m to the power 4. M cube multiplied by minus 1, we get minus m cube. And here this is minus 7 cube. So we multiply here 6m square. If minus 6m square multiplied by m, we get minus 6m cube, and m cube multiplied by minus 1, we get minus m cube. So this is minus 7m cube. Here minus 6m square multiplied by minus 1, we get plus 6m square. Here 18m square, so 12 is less, so we multiply here 12m. So 12m multiplied by m, we get 12m square, and here minus 6m square multiplied by minus 1, this is plus 6m square. So 12m square and plus 6m square, we get 18m square. Now this 12m multiplied by minus 1, we get minus 12m. Here this is minus 20m, so minus 8m is less, so we multiply here minus 8. So minus 8 multiplied by m, we get minus 8m, and here 12m multiplied by minus 1, we get minus 12m, so this is minus 20m. And this minus 8 multiplied by minus 1, we get plus 8. Now we taking common here m minus 1, so we get m cube minus 6m square plus 12m minus 8 equal to 0. So now we factorize this again. You can see we factorize this given equation again. Now we take this factor m cube minus 6m square plus 12m minus 8 equal to 0. You can see here m, if we put m is equal to 2 here, so this is 2 cube minus 6 multiplied by 2 square plus 12 multiplied by 2 minus 8. So this will be 8 minus 2 square 4, 4 6 are 24, and this 24 minus 8. You can see here this plus 8 minus 8 cancel out, plus 24 minus 24 cancel out, so this is 0. So if we put m is equal to 2 in this above cubic polynomial, we get 0. So m minus 2 is the factor of above polynomial. Now we write m minus 2 3 times. Now here this is m cube, so m square multiplied by m, we get m cube. M square multiplied by minus 2, we get minus 2m square. Here is minus 6m square, so we multiply here minus 4m. Minus 4m multiplied by m, we get minus 4m square, and minus 2 multiplied by m square, this is minus 2m square, so we get minus 6m square. Now this minus 4m multiplied by 2, we get plus 8m, and here 12m, so we multiply here 4m, and this is 8m, we get 12m, and this 4 multiplied by minus 2, we get minus 8. Now we taking common again m minus 2, and we get m square minus 4m plus 4. So you can see this m square minus 4m plus 4, this is also m minus 2 whole square. So here the factors are m minus 2 whole cube. So the factor of the above equation, so the factor of the above equation, so the factor of auxiliary equation are m minus 1, m minus 2 whole cube is equal to 0. So we get the value of m, that is 1, 2, 2 and 2. Here we can see 3 roots are equal and 1 is distinct. So the general solution of third order linear differential equation with constant coefficient can be written as y is equal to c1 times e to the power 1x plus c2x square plus c3x plus c4 times e to the power 2x, and this can be also written as c1 e to the power x plus c2x square plus c3x plus C4 e to the power 2x. You can see here three roots are equal. Here three roots are equal. When three roots are equal, power of x is 1 less than. So 3 minus 1, this is 2. If four roots are equal, so we can write here C2 x cube plus C3 x square plus C4 x plus C5 and so on. So this is the general solution of third order linear differential equation with constant coefficient. Thank you.